All right, welcome back. And so today, after we just went over our exercise from last week, and I did not record that on purpose. So now we've come into a little new topic today. We're going to talk about stochastic models. Stochastic. Now there are two kinds of stochastic models. I am not talking about the first one. There is a stochastic model where the X values are stochastic. That's not the one I'm talking about. I'm talking about stochastic models where the Y values are stochastic. And what do I mean by that? Well, we're going to find out real soon here. But let's go on down to the agenda here. So what have we done so far? Well, we've done linear models where we are looking for perfection, quite honestly. We have done linear models where the goal is perfection. The goal is absolute perfect match between Y and X. And every time we don't have a match, we consider that a failure. We say, it's because the data is not good enough, or our model is not good enough, or, we didn't do something right. But what if it doesn't matter how good the data match is and how good the model is and everything, and you still don't have a perfect match between Y and X? And that will happen in a lot of cases, a lot of examples. So let's see how that's going to happen. Let's see how that's going to happen. And I've got a data set. Well, just to refresh our memory here. So we have a data, our linear regression up until now has been all about fitting this model and these data points and getting this line between these data points in such a way that these distances to the line are minimized. And I don't know if I said it specifically before, but if I didn't, I apologize. But this is called ordinary least squares. And this is, we will sum these, we will square these distances and sum them and minimize that sum. And that is what the entire last 4 weeks have been all about. Now we have something different, something completely different, as Michael Palin would say. And this isn't going to work anymore. So let's see what we're going to do to make it work, what we're going to do differently. And there we go. Come on. So there's a data set on Learn that I'd like you to grab and get this data set and pull this down, and we're going to work on this together. So please go and Learn and get this. It's in the forelacing folder, data sets for forelacing. It looks like this. This is what it looks like. It's a spreadsheet, has like 1, 2, 3, 4, 5, 6, 8 columns. And it's a little extract of data from D2 transport from a long time ago, from like, I don't know, 12 years ago, from the transport undersökelse. And it's about, it's survey data. How many cars do you have in your house? How many cars do you own? How many cars are in your household? And the columns here are things like, how many Kurkort, how many people with a Kurkort live at your house, in your family, in your husten? What is the gender of the person filling out the survey? I believe is what that, I believe what I stole this data set out of an old class folder. So I didn't take the time to talk to Michael Barfool about this before I started doing it. I just grabbed the data, kind of stole it. But I believe the gender is the gender of the person answering the survey. So you might imagine that immediately that's really probably not relevant. It doesn't matter what the gender of the person answering the survey is. Hopefully they can count And the husband isn't keeping a secret car in a private garage somewhere he hasn't told the wife about. How many children live in your house is column D. What year is it? Almost all of the data is 2008, but I think there are a couple of 2009 entries in this spreadsheet. There's a column called age group, and then there's a ID and an explanatory what is the age group, and that is, I believe, also the age group, the age of the person answering the survey. And then your job status, and I believe, again, that is the job status of the person answering the survey. And then LMA is, column G is the Arbeitsmarkt status. And then lastly, the column H is the household Inkomst. And I believe that is, it doesn't say, actually. I don't know if that can't be monthly. That's annual. That's got to be annual. So that's annual Inkomst. Monthly. Yeah, 100,000 kroner, please. Ja, tak. Yeah, no, that's annual Inkomst for the household. And the numbers in this picture are really small because I sorted this. And so we're looking at this, we're looking at the top of the list where the numbers are really small. They get bigger as you go down the list. So this is the data, and I hope you've got it out and on your computer now, because we're going to do this. Let's do this together. And let me see. Let's do a traditional linear model here, folks. And I have, let's see, I've got the solution. Let me move my windows around here. I have one window with my solution already done. There we go. And then but I'm going to do it with you. I want to get R up here. Let's get this up on the screen. Where are we, mister? There you are. There you are. All right, let's do this. So same old game. We do this I think this is already loaded, but I'm just doing this to keep the video consecutive. That's already there. So now, and I deleted everything from before the break, so I can reuse all these names without messing. You make sure you don't goof it up either. So delete these names, delete your directory. X, L, S, S, come on, S, X, yes, yes, yes. And first tab, there we go. Yeah, that looks correct. That looks correct. I think that's correct. And this has something like, this has almost 8,000 records in it, this file. It's about 8,000 records, I think. Come on, still loading. Still chugging away here. Okay, now we got it. All right, didn't get a chance to drink my coffee. That's not fair. All right, so let's see what we got here. Yeah, looks right. I think that's correct. I'm just making sure I've got the right data set from my solution. It would be really horrible to go through a whole deal. And then let's look at what it looks like. And there it is. Looks fine. Good. That's all correct. Yeah. Okay. All righty. So we're doing that. And so we got that. So that's what it looks like. That's almost the same. I did a little slightly different code this time around. But now, just never enough windows. Never enough windows. There we go. All right. So now let's go straight for the high-powered high test here. Let's do a subset fitting of this thing. Let's go straight to the most powerful tool we've got. Come on. Yeah.
How many works do multi for, Stephen? Because I know one person who got it to work.
Really? Nobody else has got it to work? Well, at least you can just watch me. Even after trying to fix the R Java and everything, you couldn't get it to work. But that's kind of a bummer. But I don't know off the top of my head an easy alternative to this. We could investigate it a little bit. And is it RStudio? What happens if you do this without RStudio? Now maybe that's a question too. What happens if you do this from the console and not from RStudio? That might be a question to consider.
I mean, I tried everything with the GL Multi also in R GUI that you are using, and nothing worked with it.
All right. I might, Creston, if we could take a private Zoom call sometime, because I don't have an easy solution. I can investigate it, but this GL Multi seems to be a popular pack for this tool, for this task. And
sure, but I mean, I have tried everything, even
right.
uninstalling Java and
right.
installing it again, and everything with that, even completely uninstalling R and installing it all again. I've tried everything, and nothing with it worked.
All right. Okay. Well, if we could take a private call and you could share your screen and we could try to debug it together, because
sure.
I would like to know why. I mean, yeah, it's an interesting question why it doesn't work when it's, as far as I can tell, pretty popular pack actually for doing this. Or we can dig into it a little deeper, because I would like to make it actually a more significant part of our exercises and our work. But anyway, so just follow along here and we'll figure this out. Here we go. And I'm going to, how am I going to do this? What's the easiest way for me? Oh, I know what I'm going to do. Here we go. I know what I'm going to do. This is going to make it easier. There we go. This is what I'm going to do. There we go. Perfect. Yeah, it'll speed me up a little bit. Oh no, it's still not going to speed me up that much. I still have to type it in by hand. All right, here we go. Anyway, okay, and all right, here's the command. Oops, come on. Yes, car tilde. Keyboard change, back again. And data equals my data. Method equals yes. And we're going. There we go. Good. And then all right. So this is, as we've learned from our previous homework or whatever, this particular set of commands, this particular tool is very likely to give me very quickly, without a lot of deep thinking, a very good model, to start with. And anything I do beyond this would be kind of tweaking and polishing. Maybe some data transformation would make a difference here. If I did some data transformation, that might make a difference. But what do I got here? I've got a model with very high significance and an absolutely horrible R squared. Absolutely horrible. I mean, just dreadful. And so So I have a model that's telling me that yes, your data is significant. Yes, your data is important. This is good data. But it's also telling me I cannot create a linear model that promises you, that actually delivers for you, that I can prove y equals x. I can't do it. I really can't do it. And so let's look at the plots. Come on. Let me get this back, get that back, get this back, plot. Wow. This is like, oh, this is like, what am I going to do with this? Right? So this is a problem. This is a problem that, we look at this residual and this is like not supporting our model assumptions at all. I mean, this is a bold, blatant. I think what's really striking about this is this idea that there is this clear, for the exact same fitted value, for the exact same functional location, you have very clearly very dark and very distinct duplication of all three potential response values. So the response values are 0, 1, and 2, and this thing has scaled it. These are this is the residuals. So there is basically, looking at this picture, there's basically like a 50% chance that this thing gives you the wrong answer, up or down. And so this is not especially useful. This is not really very useful in our thinking about what we're doing here. So the question is, okay, is it the model, or are we just not thinking straight? And I'm going to tell you now that the answer is we're not thinking straight. And there's a totally different way to look at this data, which I'm now going to describe. There's a totally different way to think about this. So let's talk about that. Let me clear this and get rid of this. And oh, there's our residual. Now residual, our normal probability plot looked great, right? So this is like, all of this other stuff is pointing in the direction of saying, hey, great job. You got good going. But then when you look at the actual the power of this model to actually predict something is horrible. It's just a disaster. And the answer is that this is the wrong model. The answer is this is not the right tool. This is not the right tool to do this. It is, the data is statistically accurate. The data is statistically relevant, but this is just the wrong tool. This is just the wrong tool. So what is the right tool? Well, let's figure out what the right tool is. Let me close this up. I'm done with that. Thank you very much. Close that. Okay, we're done with that. I'm going to put the presentation back up here again. And I've already done that. And here we go. And let me get this window open. Come on, anytime now. There we go. So so here's our presentation again. So we already talked about this. I already said this. And so what's really going on with this data? So I made this in Excel. I actually had a little help. I also massaged the data in a database program. I probably could do this in R somehow. I just don't know how. There's probably some magic number of combinations of commands that I could have done to organize and sort this data. I just don't know what they are. But I do have the skills in database technology. So I put the data in a database, or ran a sub-summary report, exported the data back out to Excel, created this bubble chart. So this is a bubble chart of the car ownership. And I'm just looking at one X value, just the driver's licenses, just as an example. And what you see here is that there is no magical I mean, there's a little bit, there is a trend. I mean, there is a trend. I mean, there is a trend. Clearly there's a trend, but it's not the kind of trend that you can just draw a straight line through and say, okay, problem solved. I figured it all out. It's still for every level of the explanatory X, for every level of X, there's still kind of a randomness. There's a randomness. I mean, for a house with 2 driver's licenses, it's still possible that nobody has a car for whatever reason. Could be they're retired. Could be they have their driver's licenses, but they live in Norhound and they don't need a car, or they live in Christianshavn or something. You know, they don't need a car. They use a bike to move all their marijuana around or something. I don't know, but or they have 2 cars. But then clearly there is a trend where the largest majority have 1 car, 2 driver's licenses and 1 car. And then when they get 3 driver's licenses in the house, then clearly they have a hard time. They fight with each other all the time about who gets to drive the car. So a lot more of them have 2 cars, right? And et cetera. So there's clearly some influence, but it's not clearly cause and effect. So the point being here, we need a model that is willing to consider this as more of a random behavior and not as a direct cause and effect. And so what I mean by that is we need a model that can export this, can create a solution that is in fact a probability distribution. So our answer, we're now no longer looking for a model that says X1, X2, X3, I put the numbers in and that's what the value of Y is, I'm all done. We're looking for a model that says X1, X2, X3, put the numbers in, and the answer is maybe. The answer is, here's a probability distribution of what the choices could be based on the X that you have. And we will see this in great detail here as I move through this demo. So we want to predict not the value of Y. We want to predict the probability distribution of Y. And we want to have it in such a way that for every one of those households, for every one of those houses that answered this survey, we take the answers they gave on the survey and we plug them into the model. And the model returns a probability statement that says, based on the data you gave me, I predict with this much probability that they have 1 car. And I predict with this much probability that they have 2 cars. And I predict with this much probability they have no cars. And so I'm now not looking for a specific value of Y. I am looking for a probability distribution for Y based on the answers in the data set. And how do we do that? Well, we have this thing called the multinomial logit model. This is chapter 13 in your text. And it's structured like this on the screen right here. What we have is, for this particular example, I have 3 choices. I have 0, 1, and 2. But you take the same model and you just keep extending it. It could be 0 and 1, or it could be 0, 1, 2, or it could be 0, 1, 2, 3, or whatever. You could just make it as big as you want for how many choices you have. But we want to create a prediction of the probability for each level. So this is the probability that there's no cars, probability that there's 1 car, probability that there's 2 cars. And we want a separate probability for every single data point. So this n is the number of the data point. So this data set has like 7,800 records. So there is going to be a distinct and individual probability, one probability. There's going to be a distinct calculated probability for every single one of those 7,800 records in the data set. How are we going to do that? Well, we're going to have a structure that looks familiar now. So this part right here, that part is our linear regression model. That is our linear regression function. So we have the X data and we have coefficients. We have a linear function for that relationship. But now instead of having one set of coefficients, we're going to have a separate set of coefficients for every level of Y. So this is the coefficients for the probability that there are no cars. These are the coefficients for the probability that there's one car. And these are the coefficients for the probability that there's two cars. And then this formula, and then you're on the bottom, you sum up all the possibilities, and that's the denominator, the bottom part of the division. And then the top, the numerator, the top is going to be the probability for this one condition. So we'll see this here some more here in a minute. And I do want to apologize a little bit for the text. I should say this now. When we get to chapter 11 and 13 and 14, these chapters are at a level of math that is honestly too high for you guys. That is, if you guys are reading those chapters and you're like, I have no idea what this guy's talking about, that's okay. Those chapters, in my opinion, are way too advanced in their mathematical language and in the way they present the material. I think they're way too advanced for a diploma level course. Those chapters are written at a graduate level, at a graduate mathematics level. So if you're reading those chapters and you're like, oh God, this is too much, I can't figure this out, that's okay. So my job is just to try to point you in the direction of the most important things in those chapters and give you a tool to do some of these calculations. And that's it. That's all our goal is here. I'm not expecting you guys to like know the theory. Now that's different from linear regression, because linear regression, the mathematical level for linear regression is lower and the concept is simpler. And so in linear regression, yeah, I think you can do that. In linear regression, in our presentation, I go into some of the theory and I show you the formulas, and we even manually calculated some stuff. But in this part, for this stochastic dependent variable, for this stochastic response function, yeah, the math is a lot higher. And so you don't need to be all stressed out if you're reading through this chapter going, wow, there's a lot going on here. It's okay. So, but my job here is just to point out the kind of the highlights, just the most important points in this subject. So anyway, so let's go to the next slide here and see a little bit more about how this is going to happen. So here is, I kind of already said some of this. So, so here's an example. This is what each one of those statements is doing. So the bottom, the denominator is the sum of all the possible model components. This is everything at the bottom here. And then the top here is the set of coefficients for the one condition. And then this is the data point, the one data point for that, for n, data point n, the one data point. So, and then we are going, this is exponent, this is power of e. So this equation is this linear function to the power of e. And the same thing down here. This is the sum of each of these to the power of e. So that's what's going on here. Now this matches exactly, this is equation 13.21 in your text. So I'm pointing you to the text. I made a change to the way it's written on the screen. You'll notice there's a little bit of a change in the subscript. I think the way that the author wrote this formula in the text is not, it's at the minimum, it's really confusing, possibly wrong, depending on what argument you want to make. In my opinion, it's harder to read than the way I wrote it here. And this is more in keeping with what you will find if, for example, you look at this on Wikipedia, or if you look at some other sources. So yes, there's a small difference between what I wrote here and what's in your text. And I think mine is more accurate, more easy to understand. So anyway, so now you can see is that we have in our data set, we've got 7x columns, 1 y, the count of cars is y, and then all the explanatory data is x, and there's like 7 of those. So we need 7 coefficients for every one of these levels. So there's going to be 7 beta coefficients for the probability that there's no car. And there's going to be 7 coefficients for the probability that there's 1 car. And there's going to be 7 coefficients for the probability that there's 2 cars. So we're going to have 21 coefficients in this function. And we need to fit these things so that we have a nice fit of this to all these 7,800 records. And that ain't easy. It's not easy. And it can't be done. It cannot be done with just like your calculator and some numbers in the spreadsheet. It can't. It's not possible. It mathematically, theoretically, it's not possible. So how are we going to do this? So previously we had ordinary least squares. That's a nice simple math. It's very easy to understand. You can just generate some answers with your calculator. Now we need to do some kind of best fitting, and it's not easy at all. It's not. And it requires computers. It's a very intense computational thing, which also explains why this field of regression is, in the big picture, relatively new. It really originates from like, I mean, it's theoretically 40, 50 years old, but nobody had the computing power to do any of this until like 20, 30 years ago. So as an application out in the field, it's relatively young, and it's relatively it has fewer tools, and there's more chance for people to disagree with each other. When you Google this and read about it online, you start to find disagreements. You start to find things that are presented differently, and part of it's because they don't agree with each other. But anyway, the key rules here are that all of these probabilities are non-zero. So we have there are no zero probabilities. All the probabilities are non-zero, and they all have to add up to 1, which kind of makes sense. So the probability of having no cars, the probability of having 1 car, the probability of having 2 cars, the sum of that has to be 1, has to be 100%, right? It stands to reason, but that is part of the math that is guiding the derivation of these coefficients. So how are we doing this? We're going to use something called a likelihood function. And a likelihood function is a very nerdy statistical concept. A likelihood function is, I have some function that I want to fit. I have some probability distribution, and I have a set of data. I have a bunch of data points. And a likelihood function is, what is the probability? What is the likelihood that if I have this distribution, I would have picked these sample data points? And in a very simple way, you could exercise this. You could say, okay, I start with data point 1, and I calculate what is the probability of having pulled that data point from this distribution. And then I go to sample 2, and I say, what is the probability that I pulled that data point from this distribution? And then I go to sample 3, and I say, what is the probability I would have pulled that data point from this distribution? And I keep going, go, 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 go. Then all of those probabilities, what is the joint probability? Now the joint probability is the multiple of all those probabilities. So if the probability of picking the first one was 50%, and the probability of picking the second one was 10%, the probability of picking both of those is 5%. Because there's a 50% chance the first time, and then the next time it's a 10% chance, and the probability that they both happen is 10% of 50%, which is 5%. And you keep on going down the line. So these joint probabilities, these likelihood functions are very small numbers. They are very, very small numbers because you're talking numbers that are, some negative exponent, because they're all less than 1 and you're multiplying them all out over a long range. So you end up with these really tiny numbers. But the higher the number, the closer the fit of your data to whatever probability distribution you're trying to fit. And there's an example here. I'll give you an example here on the next screen right here. So this is the likelihood function. And this symbol, if you've never seen this before, this symbol is like a summation, but you're not summing. You're not adding things together. You are multiplying. So this symbol says, take the first one, multiply it by the second one, multiply it by the third one, multiply it by the fourth one, and keep on doing this until you get to the last one, until you get to n. So it's a string of all these terms multiplied together. That is a likelihood function. And there's some examples of what this likelihood function looks like in your text on chapter 11 and chapter 13. So I'm pointing to where this theory fits in your textbook, but the description of those likelihood functions in your text is very, very intense. It's very intense. You need a couple of cans of Red Bull before you start reading that, folks. So, but it's very intense. So I hope I'm simplifying this for you a little bit. So the problem is that so the goal here, now for every one of these, for these distribution functions, there are parameters. There's some kind of parameter that fits that distribution function. And so the goal here is you string all these points together in this likelihood function. And the goal here is I want to figure out what the parameters should be so that my likelihood function is as high as possible. And now that gets hard. Now that gets tricky because you got 7,800 data points, and every time you tweak these coefficients, the numbers start swinging all over the place, and then the likelihood function starts bouncing all over the place. It's nonlinear, so good luck with that. So it's very intense. This is mathematically very intense. It's very high theory, and you got about as much chance of doing this by hand on your calculator as you got as you have of going into your kitchen and cooking up a semiconductor on the stove. It ain't gonna happen. It's not gonna happen. So we need to use software. So we need to use these tools. And let me clear this and clear this. And so let's go and let's do this. What time? What are we doing on time here? Let me check my clock. Okay, almost coming up for another break here in a few minutes. Let's see. Let's just get the data warmed up here a little bit. But the most basic tool we're going to use here for this activity is a pack called multinom. And I actually had a very stressful time getting prepared for this lecture because now we're starting to creep out of my zone of comfort here. I don't have a reason to do this kind of analysis in my field. This kind of analysis is more typical of like opinion surveys and surveying people on what their favorite brand of pizza is or something. This is more marketing based. This is really marketing and consumer demand studies is really what this is really, because there's this enormous in marketing and consumer demand, the people making the choices, there's a lot of emotion in that, right? There's a lot of emotion. And, you know, why do you like a green car instead of a red car? Well, there's no formula that's going to tell you this is why this guy wants a green car and not a red car. It's a random emotional component. And so this is about marketing, and here in transport, we're primarily concerned with things like, what is the emotional draw of a passenger to choose bicycle instead of light rail? Or what is the percent desire for our passengers to purchase first class instead of second class, right? Or how likely are our passengers likely to purchase a hot dog and a Coca-Cola in the cafe car on the train, right? This is all, there's no magical formula that's going to say, yeah, well, that passenger is going to buy a hot dog. It's not, no, it's random, kind of a random effects model, right? But this is, I don't do a lot of this. I don't do any of this actually in my research. So I'm a little bit more dependent on textbook and things like that. And when it came to R, I struggled a little bit. There's multiple packages that do this kind of analysis in R. But I ran into a lot of problems. Some of them are really, really picky about how the data is structured, and they do not tolerate any errors at all. And when I was online researching this, I found lots and lots of complaints and calls for help on Stack Exchange and stuff, where people are saying, I can't get my data to work. I can't get my data to work. And that seems very typical. So this multinom package is the oldest. It is the simplest. It's also the least powerful, but it's also the one that has the fewest complaints. It's the one that the fewest people complained about. And it seems to be the one that is most tolerant of mistakes in your data. So I'm focusing on multinom as our tool of choice here. There's some other tools. I had a hard time getting them to work with the data sets that I wanted to use. They work great. They work great with the sample data that came with the pack. If you're just using the model that they sent you, it works great. But to get it to work with my data, no, I couldn't get that to happen. It was very stressful. It was very difficult. And, you know, if we were doing this in SaaS, I bet this would all be solved, because SaaS is, you know, all about customer service and friendliness, and they just figure it out. But R is not, obviously. So anyway, let us take a look at our data a little bit in R, and then we'll take a break here in a few minutes. We're almost ready to start the clock on a break here. But let me just pull, let's do this. This is what I'm demoing here. Let me kind of pull this up here. So let's take a look at our data one more time. Yeah, let's take that. So here's our data. Come on, whoops, there we go. This is a funny command. This is called structure, str, and it tells you the structure of your data. What kind of field is it? What's going on with the data? Stuff like that. So we got 7,800 rows of data, and we have 8 variables, as I said, and we need this multinom package, which is actually built in. That's another nice thing about it. This is actually built into your standard R installation. You do not need to install this as a separate thing. This is actually going to go pretty quick here, but let's do this. The package looks like this, so let's try this. Let's see. Have we got other packages laying around? Let me see. Let me clean up my workspace. Good, that's fine. Okay, that's good. So let's do first result, multinom car, and So this is also another nice thing about multinom is it's very friendly to just the default setting. You can just quick, type in your model and your data and go. The other packages, you know, you had to do all kinds of stuff. There were all kinds of things you had to put in the command line to make them work. So multinom's a little more user friendly in this respect. So I do that. And what did I do wrong? I did something wrong. What did I do? I know it works because, I do need to load it. All right, maybe I do need to load it. Okay, what am I doing wrong? What am I doing wrong? Interesting. I actually saved my results. I know this works because I saved my results. I am putting a typo in here somewhere. Somewhere I'm putting a typo in. What am I missing? What is this? I'm missing a pack. There's a pack I'm missing. Let me check my notes here. I must have left something out in saving my notes. I left something out here, folks. Sorry. I apologize. I did not write that down. What am I missing? Oh, I got it. It's this is what we're missing. Come on. Case sensitive. Thank you very much. There we go. And I think we're okay now. Yeah, let's try it one more time. Oh, there we go. So we need the pack NNET, NNet. You need the pack NNet loaded for this thing to work. I'm going to make a note of that. That will catch me if I don't get that next time. Let me write that down. Anyway, this is a good time to take a break. Let's take our 10-minute break now. And we'll come right back and see what happens to this thing, how we analyze this. So let's take our break. See you in 10 minutes. We're back. We're back. All right. So anyway, so we got this. Let me get this. Too many screens, too many things. There we go. There we go. So let's take a look at the summary here of this result. Yes, and there it is. So there's our answer to this fitting of these values, and these are the coefficients. Whoop, that's not very pretty. Okay, let's try this again. This is the coefficients for cars equals 1, and this is the coefficient for cars equals 2. And then there's an intercept, and then there's a coefficient for license, and a coefficient for gender, etc., and down the line, and all the way. These are the coefficients. Now there's no coefficients shown here for cars equals 0. That is because this program starts out with cars equals 0, or the first choice. The first choice in the list is assigned a 0 coefficient. So all of these others are in reference to the first one. So the first has a 0 coefficient, and then cars 1, cars 2, those coefficients are with respect to the first in the list. So the first is a 0, and we will see what that looks like here in a little bit. So these are the coefficients. And then these are the standard errors of the coefficients. And then we've got an AIC down here, but it's not really that useful on its own. The AIC number all by itself doesn't actually mean anything. It's only good when you're in comparison to another AIC number. So it's not really much use to look at just one AIC number. It doesn't really do anything for you. So what else can we do here? Let's see, what else do I have? what other little toys do I have to show you? Oh, let's take a look at this. Here we go. Let's look at the significance of these guys. We need another library for this, and you will probably have to install this. In fact, you will have to install this. I know for a fact you will have to install this. So there's a pack called AER, AER, and it's all caps, Storbosteo. Library, and I've already installed this, but you will have to install it. You're going to get an error message saying install this pack, but and it has a lot of dependencies to other packs as well. So sometimes I think if I do it a second time, it's sometimes I think yeah. So the first time it gives you all these warnings about the stuff it needs to have. The second time is like, yeah, I got it. I'm all good. So we need that pack, and then there's a coefficient test. So we don't know what the significance of these coefficients are yet. So we need to calculate this, and this pack makes it easy. So coef test first result. And here are the significance of these coefficients. Here are the significance of these coefficients. Now this, I think I'll switch back to the slides. Because I've got some comments on the slides. So here are the slides. This is just the same as what I just showed you. This Z value over here, this is the critical, this is the test statistic right here. This is the test statistic. And that is the test statistic that's in your book in the chapter. And this is equation 13.29. This is the test statistic in your book for this subject. So this command is calculating this test statistic. And then it's telling you what is the p-value of that test statistic. And you can see here that we have very good p-values on this. Notice something interesting. That, we have two sets of coefficients. We have a coefficient set for the car equals 1, and we have a coefficient set for the car equals 2. So see this? So what's interesting is that the coefficient could be not significant for car equals 1, but it could be significant for car equals 2. So this is a weird thing here where we have the same data, the same variable showing up as significant in one area, but not significant in another area. So this is another example of how complicated this is, how much more there is to worry about. And so you might have this decision if we haven't even begun to talk about making this model different or better by dropping variables or transforming variables. We haven't even touched that. But you can see this is going to get complicated, because if I want to consider dropping the variable LMA, well, it's not significant in one group, but it's very significant in another group. So should I keep it or should I drop it? That's hard. That takes a little bit of work to figure that out, to decide. And part of it is just trial and error. We just drop it, rerun the model, and see if the model gets any better or worse, or how much worse it gets. And then, gender is a gender here and gender here. Gender is clearly, and which stands to reason, what difference does it make whether the person answering the survey is a man or a woman? It might make a difference. What the survey doesn't tell us is, okay, if we look back at the data in the survey, actually the survey data does not tell us how many people are in the house. We know how many children there are in the house. We know how many driver's licenses there are in the house. But that doesn't say how many people are in the house. Could be there's one driver's license, 2 children, but there's 4 people living in the house. There's a 4th person who's not listed, or there's only the 3 people in the house. We don't know. So what we don't know is this a house with a, well, in this modern day and age, we don't know, is this a house with a single parent? Is this a house with one adult who is either a man or a woman? Or is this a heterosexual couple with a man and a woman? Or is this, a LGBT couple with 2 women or 2 men or whatever? And so this gender component is not really very well designed in terms of telling us what influence it has on their desire to own a car. And so here up on probability of car equals 1, we can see that the gender is not statistically significant. And we can also see that it has a small coefficient. It is not the smallest, but it is at the lower 3. It's at the bottom 3. This is the smallest. This is the next smallest. And then this, so it is second to the last. No, it is 3rd. This is smallest. This is next smallest. This one is the next smallest. So this is, so gender is the 3rd smallest coefficient up here. And then down here, well, but these aren't standardized either. So I can't really, it's hard to make a comparison. It's hard to make, they're not standardized because these are not standardized coefficients. So I should not be saying that. I should not be making that comment. Never mind. Forget I said that. Don't worry about it. But this part over here is correct. This is the significance. This is the correct interpretation. Anyway, so let's go to the next slide. And I won't do this live because it's not that important that I actually do it live in front of you. But you could try this at home. Here we go. So the likelihood ratio test is another thing. This is in your textbook also. This is equation 13.3 in your textbook. So you need another library again. You need the Affix library pack. And yeah, you'll have to install this. Yeah, you'll have to install this again. So you need the Affix pack. And then you run these commands that I've got here. And you need the car pack. And then you can run an ANOVA test. And it will give you these chi-square test statistics and results as described in your textbook on page 13.3. And again, now what's nice about this is telling us notice that this is telling us the significance of the variable, not the significance of the coefficient. That's this important difference, right? Because up here, we're like, what do we do? We got 2 sets of coefficients and one is significant and one's not for the same variable. But on the likelihood ratio test, now the information is presented to us as a function of the variable. So this is a little better in terms of saying, which variable do I want to drop? If I want to drop one. But based on this, they're all pretty close. They're all pretty good, except, this gender one is not, it's significant, but it's not significant in a way that makes me impressed. So it could be an argument that we should rerun this model and take out gender. Just take it out and see what we get. But that's for next week. I'm not going to do that now. That's a discussion for next week, how we do more to test whether these models are really good or not. But let's see, I'm coming up towards the end here. Let's see, what do I want to do? Oh, one more thing on this, and then I've got something to show you. Come on. There we go. Here's another function called confint. So this tells you the confidence intervals for the coefficients. And you can see here that we have, again, coefficients for car equals 1 and coefficients for car equals 2. And this tells you, how tight are these coefficients? How much certainty are we over their actual impact and their values? And then, of course, if they cross 0, that matches with our p-value discussion, our p-value measures previously. So now I want to, now I want to show you a spreadsheet. Let me show you a spreadsheet. We're coming up on the end here, but I don't want you to see this yet. Let's see. I'll just kind of put that in the background for now. Don't need that. And let's get the spreadsheet open here. Come on. And here we go. That's what I want. Yeah. Here we go. All right. So let's see. I might have a difficulty fitting this on the screen because it's a big spreadsheet. It's a big spreadsheet. Let's put this over here. All right. Let's put this right there. All right. Okay, good. All right. Now, what do we got here? Let me, I hope it's big enough. Let me just boost it just a little bit more. So what do we got here? So this is our data. Here's the data. Yeah, there's the data. And I made space up here to put in the coefficients right there. So there is a place to put the coefficients. And then remember I told you the very first choice, the coefficients are 0. That's the multinom package. When it calculates this, it references everything from the first choice having a 0 coefficient. So these are zeros by default. This is just the way it is. And then these are the values of the coefficients copied over from the result and pasted into the spreadsheet. And the reason I'm doing this in the spreadsheet is because, well, this is a lot of fooling around with data manipulation, and I want to see it visually in a way that you guys can understand really clearly. So these are the coefficients. So now what I want to do, actually, I'm going to pull the slide back up. What am I doing right now? I'll tell you what I'm doing right now. I'm calculating these formulas. That's what I'm doing. So I'm going into the spreadsheet and I am calculating these probabilities from these results. That's what I'm doing. So I've got these coefficients entered up here. And then over here on the right, for every data point, I am calculating the numerator, the top part of that probability. So I've got the top part of that probability in these columns right here. So this is, for example, and I'm using the sum product function. So this is the exponent. This is this value to the power to e to this power of the multiple of all of these coefficients against the matching data line in the data. So this is the b times the x, the b times the x. So that's what this is going on right here, plus the intercept up here. And I just realized, I think I have a type, no, yes, no, that's correct. Never mind. It's all correct. I'm sorry. I thought I saw a mistake, but I don't. No, it's correct. It's great. So this is the, so what have we got here? So as you go down, we're multiplying those coefficients by the row of data that matches with it. So we keep on going down the line here, and we're multiplying out all these coefficients and these things. So these are the numerators for the three different conditions: no car, 1 car, 2 car. Now, over here, I now want to know what is the probability that this one house with this data, what is the probability that this one house with this data has no cars? Has no cars. And what is that probability? It is this numerator here on the left divided by the sum of all three of these guys. And the same thing with the probability that there is one car. It is this value, this numerator here under one car, divided by the sum of all these guys. So that gives me now this probability table. And for every single one of these households, there is a unique probability that they have no car, or they have one car, or they have two cars. And those probabilities always add up to 1, which is what we stated in our assumptions, in our rules. When we started this process, we said these probabilities have to add up to 1. And they do. All of these probabilities add up to 1. But they're all different because the data is all different here. And so every one of these is moving a little bit in a different direction. And there's a lot we could do with this. I didn't plan any of it in advance for today, but we could look at it some more later. There's a lot of fun stuff we could look here. For example, how much is your probability of having no cars related to your income? Well, let's do that. So let's see. This is the last. This is a lot easier for me to just look and see what the number is. This is row 7860. Let's remember that, row 7860. And let's go over here and let's insert a graph. It's a scatter. Let's choose the data. And let's add some data here. There we go. 7860. Let's remember that. So that was, so this is going to be income. Let's do that. And whoops, come on. I didn't mean that. And the X values, let's make the X values income. So the X value is going to be income. And that needs to end at 7860. A lot of data points there. And then the Y value is going to be the probability of having no car. The probability of having no car. Copy. Come on. Come on. I thought I had this. Oh, I know what I'm doing. Why is it not allowing me to do this? Come on. Let's try one more time. Edit, income, X values. Yes. Interesting. Why did that do that? What is going on here? I'll tinker with this later. I don't want to do this in front of you. I'm clearly, something's goofy. I'm doing something wrong. I won't fool with this. I'll skip that. I'll do that graph for next week. But anyway, so let's just skip that for now. Anyway, these are the probabilities. And what I have done here at the top is these are the average probabilities for that column. These are the average probabilities. So over the whole data set, from these coefficients and these probabilities that I calculated, these are the average results of this whole data set. And but we'll come back to this next week and we'll do some kind of fun exploratory things with this data. I'll figure out what it is I'm doing wrong and solve that later. But here in the spreadsheet, in the PowerPoint, I have summarized what's going on here. So here we go. So so on the left is I just said, okay, how many data points in the data set have no cars? How many have one car? How many two car? And based on that, the probabilities are 7.8, 64.7, and 27.4. On the right is the same percentages that I calculated based on this whole multinomial logit regression thing. And they match. They match pretty close. I didn't check how close, like to how many decimal points do they match, but they match. And it's a nice little error checking exercise, you know, and model fitting proof that even though this model is generating all of these different percentages for every household, for every row in the data set, on average, the model is meeting the expectation. It is meeting what we think the big data set should do. And so that's a very good error check to say, hey, you know, did I do anything wrong? Are these results correct? So this is kind of a, yes, they are correct. So what do I do with this? You know, let's, so we're about done here for today. What do I do with this? So this is very valuable from a marketing point of view. This is very valuable from a marketing point of view. Let me give you an example of how you could use this. All right, let's suppose I do this. I'm Ford Motor Company. I am Ford Motor Company. And I have done this research for Shaylin. And I have developed this, and I have this data, and I have the addresses of these houses. I have their mailing address, and I have collected this data through, you know, various legal and illegal means. I have collected it from Google and from Facebook and from public sources and God knows what else. I've collected all this data, and then I fitted this, right? Now I have this model that accurately predicts who has a car and who doesn't. Now, look back, let me go back to the spreadsheet again, see if I can find an example. Sorry, there we go. Let's go back, here we go. Here's the spreadsheet. Here's a fun one, okay? I don't wanna mess up my data here just yet, but let's go down the list here. Let me go down the list a few points. So this column is, this far right column is probability of having two cars. All right, let's go down the list here and see if I can fit, I can't see this. This is, okay, we're still in the one car range. Okay, so right now all of this data says they actually have one car. I go over here to the right and I look at these data points. And well, wait a minute, that one says I have a 48% chance of having two cars, but in reality, I only have one car. And then I go down here, 41% chance. Let's keep on going. No, not too exciting, not too exciting. 56% chance. Nothing, 48% chance. And this is again, people who in reality only have one car. And go down this list. See, I could probably sort this, but I don't want to mess up. I would probably want to make a copy of this and manipulate the data separately. So go down the list, go down the list. Still all, oh, 53% chance. Are we still at one car? Yes, we are. But you see what I'm doing? Oh, 63. Oh, how are we still at one car? Yes, we are. So there's a 63% chance. There's a 63% chance that this house should have two cars. But in reality, they only have one car. So that's an imbalance. That's a statistical imbalance. And there are two possibilities here. One, this family, they have some attitudes or opinions or behaviors that say we are different and we are not going to have two cars. Or Or this is a family that has recently had a change in their lifestyle. Maybe their child was just born. Maybe he just had a raise in his income. Something else changed. They've had a lifestyle change, and the data is lagging the reality. So they have one car, and the data suggests that they really should have two cars, but they only have one. So if I'm Ford Motor Company, this is the family I want to send an advertisement in the mail to. I want to find all of the families in this list that have a high percentage of having two cars, who in reality only have one car, because there's a strong possibility that these families are in the process of changing their life and will in fact purchase a second car in the future. They just haven't done it yet. And so there's a much higher shooting ratio. There's a much higher probability from this data that I will succeed in selling another car to these families with high percentages for the second car when they do not in fact already have a second car. And so that is one way that this data is very useful, because it's a lot cheaper to spend money printing and mailing sales brochures to the 10% of this list that fit that criteria than it is to send it to all 7,800 people, right? And this is also the way things like marketing on Facebook work. Algorithms on Facebook that decide whether they're going to show you advertisements for Coca-Cola or advertisements for sexy lingerie. You know, they're going to look at the data and they're going to do a percentage, some kind of a multinomial logit like this. And they're going to say, based on your profile, based on the data about you, what is the probability that you would be interested in these certain products? And then they're going to use that to judge which advertisements that they put in front of you. So this is modern data analytics here. Now for us in a transport environment, this is about things like predicting the likelihood that if we build a new light rail line into a town, what is the probability that people in that town will use the light rail? And so we collect all this data and we create a probability matrix that says, here are the probabilities that they will use different forms of transport. And from this model, we could say, we predict that some percent of this town's population will in fact use the light rail. And that is part of our demand modeling. That is how we start doing some demand modeling. Or at least not we, I don't do that. That's not my research area, but other people do that. There are people who do that at DTU Transport, at Transport DTU and other things. This is their thing. This is what they're really into. And this is one of those important tools that they would use. They would collect all this data and then develop distribution profiles of how the behavior of these people function, and then use that to predict what that future demand would be. So that's what this is all about. So we're done here. Let me conclude. So this is, again, I said this is a relatively, 20 or 30 years is not a very long time in the theoretical world of mathematics. So this is a relatively new field, and you will find the vocabulary, the names of things is not necessarily clearly defined. So you will find this called logit or logistic in different books and texts. It's the same thing, but you will find it named different things in different places. There is another refined method to do this. I don't think we will do this in this course this semester, but there is a way to refine this model in chapter 14, where it's called the ordered logit model, and it gives you a little bit more accurate result. It gives you a little bit more power, but we're not going to get to it. We're not going to do it. Next time, so next week, we will look more about this goodness of fit. And we will start considering things like, hey, should we drop some variables? Should we run this model with fewer variables? And how to compare the results of those two models. And then we will discuss something called the Poisson regression model, which is related to what we just did. It's similar. So it's theoretically the same thing. It's just a different tool. And that brings us next week is week 10. And then we realistically then have 2 more weeks after that of real content before the final week, which is always kind of throwaway week in the semester. So we have 2 more weeks after that. And I'm, I think we'll probably spend some time looking at more published papers, and maybe we will have time to look at some things like the Hessian matrix, the hat matrix, outliers, maybe some more transformation techniques, maybe some more analysis of things. Yeah, there might be some time for us to do that. So
when will we, Stephen, when will we get assignment number 4?
Let's see. It is due in
the 28th, so it's due in
2 weeks.
2 weeks.
Yeah.
Will we get it before the next lecture? So if we have any questions, we can ask you next lecture, or will we get it like last time, where we get less than a week?
Part of it is because I want to make sure that what I put in the lecture supports the assignment. So I haven't written next week's lecture yet, so I don't know what's going in the assignment. I'm kind of writing these as we go. And then, but I'm in a position where, yeah, but I won't have it out. So for example, I won't have it out this weekend, but because I want to make sure that I distribute a quality assignment that's tested and, isn't got a lot of mistakes in it or something. And I've got to coordinate that with what is the content of next week's lecture. But I'm pretty sure it's going to be exactly what we've just done today and next week. It's going to be, here's some data, fit a multinomial logit model to it. Here's some data, fit a Poisson regression model to it. Comment on the results. I do not have another data set from a published paper at the moment, so I don't have the ability to do another one of those. So it's going to have to be a data set from some textbook or public source or something. So yeah, that's where we are with that. Yeah, I will have to. It won't come out until I've written the lecture for next week, and then I've got to write the assignment to go with it. Yeah. So it'll be, it will come out next week, and you'll have a week to do it. Yeah. Yeah. So,
can I ask you something related to the freight, the goods transport, freight transport? On inside Kursusbasen, it said that the exam date is the 31st of May, but on Learn it says the 21st. When we already have exams the 18th and the 20th. So having the 21st will mean 3 exams within.
So the date that I put on, or the date I put on, is wrong.
Oh, one of them is wrong because it's
one of them's wrong.
I'm just saying that it's submitting a video, so it's not.
Yeah, like, it's not. You don't actually have to be physically present.
But it's just more that it's having 3 exams within 4 days, and me and some of the other students has a exam the 4th day also, which is a re-exam of one from December. So that means that 4 exams in 4 days will be kind of hard, even if it's only a video. So the 21st is one of those. Yeah, I'll think it's yeah. I'll prefer not to have it.
That's a common problem everywhere I've ever taught, every university I've ever taught at.
I know.
There's always that, how do you schedule exams? How do you avoid too many conflicts? I mean, I just follow the universities that, it's the university that sets the date. I don't set the date.
Okay, so it's so the 31st is actually the date, since that's the one that's on D2 Insight and
Well,
Crucis.
let's just check it one more time. I find out if I did something wrong, or did I put it in wrong? I don't know. I'm pretty good about doing something as basic as just checking the darn calendar to make sure I got it right. But let's just
Er det ikke
check it one
den
more
18.
time.
vi skal op i det her?
Hvad siger du?
Er det ikke den 18. maj, vi skal op i det her? Og så det fag, det Tue snakker om, det der om onsdagen.
Ja, men det er også den, han kigger på nu. Han kigger på godstransport.
Ja, det kan jeg godt se, men det er bare fordi, at skemaplaceringen ikke passer, fordi at det er jo, ja, den siger, at det er noget andet i kursusplanen, nemlig i den.
Så det skal være nej. Sidste dag i maj? Nej.
Ja.
Jeg kigger indgang. Er det sidste dag i maj?
Ja, det er den, der er der, ja.
Undskyld. Men ja, okay. Ja. FMB. Og det bliver sidste dag i maj. Okay. Sidste dag i maj måned, og jeg har skrevet en er det fordi har jeg talt dag for det andet kursus, det er det måske være. Er det fordi jeg har talt det andet dag for det andet kursus? Det kan være, det kan give mere mening. Nej, det her er samme dag. Okay. Okay. Jeg har faktisk ikke skrevet en dag. Hvor er den anden dag?
Gå lidt ned.
Okay.
Der står den 21. maj, individuel videooplæg sættes YouTube inden mødet.
Okay. Den file. Jeg tror, det er en file. Det er ikke 21, det er 31.
Okay.
Jeg tror, det er en file. Det er en file.
Okay, super.
Ja, hvis vi kigger på bæredygtig, eller ja. Jeg undrer mig, hvis bæredygtig har gjort det samme. Eller jeg mener, det er til Lyngby. Det kunne være, at jeg har talt data fra Herlios's plan. Cursus plan. Nej. There we go. Okay. Han har bare skrevet X. Okay. Okay. Så jeg tror, det er en fejl. Jeg tror, det er faktisk 31. Det sidste dag i maj. Jeg skal bare sende en meldelse ud, og jeg skal huske at tage en snak med Samuel, at vi har det rigtigt. Så det sidste dag i maj, og det, okay. Ja.
Jeg skrev Jeg skrev til Samuel, at han sagde, at jeg skulle snakke med dig.
Okay, ja, selvfølgelig. Varm kartoffel. Vi skal bare passe det til det andet. Ja, det er fint. Ja, det er en typo.
Når vi kommer tættere på i godstransport, så kommer der en dag, hvor du forklarer, hvad du vil have med det der med at uploade den på YouTube, ikke?
Ja, det er Samuels project.
I Supply Change Management i december, der lavede vi bare en Zoom-video, og så lagde vi den op ind i Løn. Altså,
ja,
det kan vi vel bare gøre på samme måde. Der er vel ingen grund til, at vi kommer ud på YouTube og lægger alle sammen til vores
det er rigtigt.
Vi har lavet på Insight, men ja.
Det var, den her Learn er ny til mig, og det var for flere år siden, eller få år siden, vi havde ikke video upload, så det var nødvendigt at benytte YouTube. Men i dag, vi kan sagtens gøre det på de 2 learns, så det er ikke nødvendigt, at vi skal sætte det på YouTube. Især når vi taler om individuel video, som er mere examensagtig end presentationsagtig. Så det er også ikke nødvendigt, at vi benytter præcis YouTube. Vi kan bare gøre det på Zoom. Eller på Learn. Men ja, jeg skal bare forklare med Samuel, at datoen er faktisk sidste dag i maj. Og men det er Samuel, som har erfaring med at lave en eksamen, sådan at det er nogle valg-eksamensspørgsmål, og han vil tildele disse her spørgsmål på nogle mål, og den du trækker en lol-seddel eller noget andet, og den du laver en video på den spørgsmål, og det der.
Ja, vi har gjort det med Samuel i et tidligere fag, der fungerer det meget fint.
Så Samuel har styr på det. Samuel synes, at det fungerer fint. Men jeg holder bare til Samuels erfaring, og Samuels vejledning på den her. Men jeg skal bare rette vores kursusplan, så det viser det rigtige dato. Og som ellers er det fint. Så er det fint, så det 31. det sidste dag i maj er helt fint. Er det okay? Sidste dag i maj?
Altså, jeg synes, hvis det stadig kan blive den 21. i stedet for den 31., så synes jeg, det er bedre. Men
det er bedre til 21.
Det synes jeg.
Nej, slet ikke. Altså, 3 eller 4 eksamener på 4 dage vil jeg. Nu står det på Insight, så må det jo, altså.
Ja, det er bare fordi, vi har jo allerede lavet rapporten inden.
Ja.
Og det er jo bare den, vi skal forsvare på i en 5-minutters video.
Ja.
Så jeg synes, det vil passe bedst den 21. Men det er bare min.
Det er desværre, at hvis der kommer noget pres på mig, at jeg er nødt til at holde til officiel dato, så hvis det står op, at det er 31 i forhold til universitetskalender, jeg er nødt til at følge med. Jeg kan ikke selv ændre det, uden at jeg får flere klager fra jer. Så desværre, det er bare en fejl i kursusbeskrivelse af kursusplan. Og så det er faktisk 31, og jeg er nødt til at holde til det på grund af regler og eksamenskalender det hele. Så sidste dag i maj, det bliver, jeg skal bare rette det i vores kursusplan og sende besked til Samuel, så at han er klar over, at det sker på den måde. Så så tak for i dag, og